All right, excellent. Hi, my name is Brant Robertson. I'm an assistant professor of astronomy here at the University of Arizona. Welcome to Tucson. If you have any questions about the talk, feel free to get a hold of me at brant@arizona.edu. So today I'm going to tell you about numerical astrophysics at the University of Arizona. I'll be telling you a lot about the research that my group does, but also research that other researchers here at the University of Arizona are currently undertaking. And we're interested in a wide variety of problems. My specific interest is in galaxy formation, the formation and evolution of galaxies like our Milky Way and other galaxies throughout the universe. And in order to achieve some progress in numerical astrophysics, we apply a wide range of techniques, computational techniques, to our tasks. And so, it's not only about doing high-performance computing, but it's also about physical understanding. We want to push in both regimes. Here, I'm laying out a few problems these are all simulations, actually, that I've done myself. I've worked in a variety of these areas. We really are trying to push the forefront of human knowledge in astrophysics, but we're also trying to push the forefront of human technology at the same time. So hopefully this talk won't seem too out of place for that reason. Okay, so in the context of galaxy formation, there's a very large number of physical processes that you might be interested in. So here I have galaxy formation at the center. Galaxy formation involves the formation of dark matter halos, the cooling of gas in the universe to form galactic disks. Those galactic disks, the gaseous components then form stars. Stars can go off as supernova and heat the surrounding gas that has some feedback effect on the surrounding material. Supernova can leave behind black holes that then can grow to form extremely massive black holes. We call them supermassive black holes. Those two can have feedback effects that disrupt gas in the galaxy. I'll show you some of these other physical processes as I go on. You look at this large number, this is just a sampling. There are people doing numerical simulations in every single one of these topical areas in astrophysics. So numerical astrophysics, doing computation, is something that is a widely practiced approach to doing astrophysics nowadays. And so at almost every research institution in America, if you go and you ask, what's your theorist doing? Many of them will be doing computational astrophysics. So today I'm going to tell you about 3 different areas of computational astrophysics that I'm working on myself, and then I'll mention some computational big data applications of the Large Synoptic Survey Telescope that's going to be built and operational by 2020. The University of Arizona has a large part of that, a large hand in that. And I'm also the principal investigator on a large NSF MRI program to acquire a new supercomputer here at the University of Arizona based on coprocessors. If you're interested in hearing more about that, please come see me after the talk or send me an email. Okay, so cosmological in-body simulations. What do we mean by cosmological in-body simulations? Well, structures in the universe like galaxies and groups of galaxies and groups of galaxies, we call those clusters of galaxies, and then even larger structures in the universe. We understand the formation of these structures through simulations. So what we do is we set up a particle distribution with density fluctuations, very mild density fluctuations. You can barely see them in these initial conditions. Those density fluctuations grow through self-gravity. And in a particle-based realization of the universe, you see these, the cosmic web, this large-scale structure of dark matter halos that form in the universe. And galaxies actually are thought to form at the center of these dark matter halos. Okay, so to understand the structure of the universe, and also the physical processes that give rise to that structure, we perform cosmological in-body simulations to achieve that. And once we've done a simulation like this, we want to analyze the simulation. We have to perform additional calculations. And so, just for some computer scientists in the room, I'm going to show you, a typical algorithmic application of standard comp sci problems that we use in numerical astrophysics to do analysis of these kinds of simulations. So you might ask, given the simulation of dark matter halos, how do I understand what's going on? How do I identify the regions that might form galaxies and then measure their properties? Well, we use what's called a halo finder. A halo finder is just a simple analysis tool that can operate on this very large data set. The largest in-body simulations that people have done up to date are about 10 to 100 billion particles, okay? And so we might want to, in order just to do the data analysis requires supercomputing tools alone. So here I've just highlighted all of the halos in this simulation, but you might wonder, well, how did I find these halos? And we really just use a very simple, one technique is to use a very simple technique called a spanning tree. So basically if you think about the particles in our simulation, here I've just made a diagram of connecting different particles in a cosmological in-body simulation. We can identify the minimal spanning tree associated with this connection of particles. And what's interesting about this is that if you look at something like a minimal spanning tree, you can see that there are certain connections that are longer than others. Okay, and what we can do is we can construct what's called a friends of friends catalog just by eliminating, say, all of the connections larger than some number. And that corresponds to a mean physical density, which is what we're looking for. We're looking for regions that exceed some kind of mean densities that might form actual galaxies. And so if I split up this spanning tree just saying, oh, throw away all the links larger than some number, I'm left behind with some groups. And those groups actually, in a simulation like this is a small spherical region within the simulation I showed you before, I can construct that spanning tree and just find the dense regions within this very large network of particles that might give rise to the formation of the galaxy. Okay, and so this is actually one of the techniques that we use to process our data, that just common algorithmic techniques that many people here might be aware of. But you know, we use them to great effect. We learn something physical just using these techniques that many people have been using in computer science for a long time. Another technique that we like to use is tessellation. So why do we use tessellations? Well, a lot of these simulations, they're particle-based. We call that Lagrangian-based. We're basically tracing individual packets of mass of dark matter through the universe as these structures form. So you can see the network of dark matter structures there on the left. Often what we're interested in doing is we want to estimate what the density of particles are. Tessellations allow us a technique for doing that very efficiently. And actually, you know, we've implemented this on GPUs, so we can, you know, just using CUDA to go in and reconstruct a tessellation of volume cells around the particles that allow us an instant density estimate for these cosmological in-body simulations, and this allows us to measure some of the physical properties of the dark matter network. And so here you can see there's a huge dynamic range. The tessellations on the far right are actually present in all of the other images. I'm just zooming out by a factor of 8 in each step. And we can do this very quickly, even though there's a large number of particles, just by taking advantage of coprocessor efficiency. So active research here at the University of Arizona in cosmological in-body simulations, one of the things we're really interested in is understanding, given the initial conditions laid down by physical processes early in the universe, how do you go from those very kind of nearly uniform physical conditions to the large nonlinear structures that we see in the universe? And can you predict, just given these initial conditions, what will happen, what nonlinear structures will form? And so here I've kind of shown you the initial conditions I showed you before, but I'm exaggerating greatly the density fluctuations in the early universe. Can we understand these density fluctuations and understand their statistical properties in such a way that we can actually predict the large-scale structures that form out of them in a robust way and understand their detailed properties? And now that we're running multi-billion particle in-body simulations as a community, we need to have the ability to process those simulations, and that also requires supercomputing resources. So we're developing techniques for doing that very fast and efficiently. So that's one of the things that we're interested in here. One of the most important themes in astronomy is that theory supports observation. So, you know, a large amount of money in astronomy is spent building astronomical facilities, either ground-based facilities like we have here at the University of Arizona. The University of Arizona builds the largest mirrors in the world for the largest telescopes on the planet, but we also build a large amount of space-based instrumentation for things like James Webb Space Telescope. We built a camera for HST, and so a lot of money is being spent in that in that instrumentation. The theorists, we don't get quite as much money as that because we're cheaper, but nonetheless, we want to support these very expensive endeavors that our observational colleagues are undertaking. And so here I'm showing you, this is a project that I helped engineer when I was a postdoc at Caltech, and now that I'm a professor at Arizona, we just got the data last fall. This is the deepest ever image taken ever by any telescope. This is an image from the Hubble Space Telescope peering back in a region called the ultra-deep field. And here you can see marked some numbers. These are the redshift, the actual redshift, of the individual galaxies. And so you can see the record holder at 11.9. This is the most distant known object in the universe, most distant known galaxy in the universe, which is around only a few hundred million years after the Big Bang. Okay, so what we want to understand from this image, which is really remarkable, it's a huge technical feat to do this. HST, Hubble Space Telescope, has been the most successful scientific instrument ever devised by humanity, I would argue. That's a big statement. But we want to understand, we can only take an image of a very small portion of the sky if we expose this deeply. This is hundreds of hours with Hubble Space Telescope. HST, in its net run, cost about $15 billion to launch and develop. So it's quite expensive, to run and operate. This is a very expensive kind of observation to take. If you're interested more, there's our website, udf12.arizona.edu. That stands for Hubble Ultra Deep Field. So we want to know how representative this part of the universe might be. And the only way of doing that is that we think is robust is to use cosmological embodied simulations to tell us patches of the sky of this size, what is the typical, say, density fluctuations in those parts of the sky? How big is the error on the number of galaxies at high redshift that we measure in the HST image? And really what this is asking, so if you just hear this is a cosmological embodied simulation with different patches of the sky, a degree scale is a little bit larger than the moon. The UDF is quite small there in the upper right-hand corner. We really want to know, how is our sample representative? How representative is our sample? If we go and measure some number of galaxies, are those representative of the whole universe in terms of the number density of them? Or, are we just seeing a weird statistical fluctuation? I know this very intimately. These are my daughters. I have triplets. If I didn't know any better, I would think that humans had babies 3 at a time. But I know that my sample is somewhat, unusual. And this is the same thing with high redshift galaxies. You have to know whether what you're seeing in the absence of other information is really representative or if it's quite an unusual event. My daughter in the middle doesn't like that joke. So, okay. So how representative is our sample? Well, we've been able to do calculations and find that this Hubble Ultra Deep Field, the deepest ever region of the sky at the typical point in the universal history that we're looking, is about 30% accurate, which is, good enough for government work. Okay. All right, so galaxy formation. So I told you only about cosmological embodied simulations. Those simulations, while they're quite sophisticated, involve only gravity, okay? And so, gravity, it's old hat. We would like to know, other physical processes that are important for galaxies where we're not, the dominant physical process that we experience in our everyday lives is electromagnetism. We understand gravity, but gravity is quite a bit weaker. So there's a lot of interesting physics beyond just gravity. And actually, galaxy formation highlights an interesting, kind of meta problem in astrophysics, which is the problem of multi-scales. So we know that galaxy formation is informed by cosmological environments. That's the upper left-hand corner. You can see a cosmological simulation with gas now. This is a halo of gas forming that will form a disk galaxy. If we go down in scale by quite a bit, by a factor of 10 or so, you can see that, there are galaxies that form, and these are simulations. These are all simulations I've done. This is a simulation of individual galaxies I'll tell you more about. And then if we look by, more than a factor of 10 below that, the properties of the interstellar gas in galaxies is highly supersonically turbulent. And so we're interested as astrophysics in astrophysics in supersonic turbulence for this reason. I'll tell you more about that as well. Okay. So this is an animation of a galaxy forming in a cosmological simulation that includes gas and star formation. This was run by my postdoc Cameron Humbles using a code called ENSO, which is a popular astrophysics code. He ran it on Kraken and Oak Ridge. And the visualization's done with a YT framework, a freely available visualization framework that people in astrophysics use. And so here we're just spinning a cube of gas that's about 100 million light years on a side, and you can see we're zooming in to a galaxy. These are all just isodensity contours that have been rendered. And you can see the forming disk galaxy. You can see it has some spiral structure. Soon it'll switch to a surface density map. There we go. So you can kind of see the gaseous distribution, the spiral arms that form inside of this galaxy. And then you can see the stellar distribution here. These are the stars that form inside the galaxy. So this is something that we're routinely doing now in astrophysics. This is not seen as a huge challenge anymore. But what we're really interested in pushing on is the physical detail of these simulations. The simulation was very nice, but it doesn't include all the physics that you might be interested in. So that pushes us to looking at smaller scales. So this is a simulation, a smooth particle hydrodynamic simulation of an individual galaxy. It's just sitting there rotating, but the physics that go into the formation of stars and the supernova rate and the heating processes within the galaxy are all quite sophisticated in this model. And we can only do this kind of calculation currently, given the resources that we have, using these isolated disk galaxy models, because we simply don't have the computational power to model the fine detailed structure of these galaxies in the context of a cosmological simulation. Right? So we do have to split the problem up and take things slightly out of context, simply because we just can't get enough computer time to do it otherwise. Okay, and so we really can now model some of the really detailed physical processes within galaxies. So this is a similar simulation that I've done. The left shows a density temperature map. The gas is color-coded by temperature. The intensity is the density. The middle panel is what's called neutral hydrogen. This is just neutral hydrogen gas, atomic gas in the galaxy. That's most of the gas of the Milky Way disk. And then on the right, you see molecular gas. This is the dense gas that actually leads to star formation in the galaxy. So if we can model these different components, these different phases of atomic gas, molecular gas, hydrogen throughout the galaxy, we can learn more and try to model in more detail how structures, how stars, say, form and what rate they form at in the galaxy. And so that's important for comparing with observations, understanding the history of galaxies like our own Milky Way. Okay. So one thing to realize, though, is that galaxies don't live in isolation. So even though these individual galaxies, we can model them in a lot of detail, just modeling a galaxy by itself is maybe not so interesting. It turns out that galaxies like our Milky Way in the future will undergo mergers. So many galaxies throughout history have undergone mergers. The Milky Way is going to merge into our nearest neighbor, Andromeda. And you can see a simulation here of two merging gaseous disks, a little bright. As these galaxies are merging together, the gas density increases in their disk. That causes stars to form at a very rapid rate. And there are also supermassive black holes at the centers of these galaxies. So as tidal torques from the interactions between the galaxies lead to these spiral features that allows gas to lose angular momentum and dump onto the supermassive black holes at the centers of these galaxies, as that gas dumps onto the supermassive black holes, it heats up and it lets off radiation. That radiation heats the surrounding gas and actually drives a wind, which you could see in this image if it were a little bit dimmer in the room. And that's really important for regulating the amount of stars that form during mergers. So we can model these detailed processes, supermassive black hole physics, the formation of stars in supernova in kind of a statistical way in these simulations. But we still have a great deal of detail that we're missing in these, even on these scales. And I'm sure talks later in the day you'll hear more about the detailed physics of supernova explosions. So we look forward to that. Okay. So supersonic turbulence, I told you that if you look at the gas within galaxies, so on even smaller scales than what I've been showing you here, we know that, that gas in galaxies is supersonically turbulent. So why is that? Well, molecular gas is quite cold. It's like 10 Kelvin gas. We know we can measure the typical velocity dispersion of the gas. We find out that it's supersonic. The gas is also very efficient at radiating. So if a shock forms, the gas lets off a lot of radiation. This allows the gas to become very dense and stay roughly at 10 Kelvin. So that the characteristics of gas in galaxies that might form stars is that it's cold, supersonic, turbulent, isothermal gas. Okay? And so that's an important type of problem that we can model in computational fluid dynamics. Here I'm just showing you a Mach 6 supersonic turbulence simulation that I've done. And I've just color-coded things so that gas that flows up is blue and down is red, and the intensity of the image is set by the density. So we're really interested in learning about the structures of supersonic turbulence. You know, what is the density structure? We kind of know that now through simulations. But in detail, how long-lived are individual features in supersonic turbulence? What are the statistical properties of supersonic turbulence? That's a difficult problem. It's something that is very hard to track analytically. In fact, there have been very, very few analytical results in supersonic turbulence. Subsonic turbulence, Kolmogorov turbulence, many people are aware of the classic results of Kolmogorov. In the last few years, there have been some new analytical proofs of the properties of compressible turbulence, which is really important. You know, it's a big achievement. And what those calculations show is that Lagrangian properties of supersonic turbulence are important. So one of the things that we're concentrating on doing now, on the left here you see, this is actually a subsonic turbulence simulation. It's what I could produce in time to show you this. You see a turbulence simulation that's driven in the same way as the previous image, just at a lower rate so that the turbulence is subsonic. In the middle, I'm showing you Lagrangian tracer particles that I've engineered into this code to trace the Lagrangian, the actual mass elements of the gas. And then what I can do is I can reconstruct the Eulerian grid on the far left using the Lagrangian particles. This is just demonstrating that you can actually capture everything in this dual way of looking at the gas, either Eulerian mesh codes or in a Lagrangian particle code. Okay, so this is going to allow us to analyze the simulations I just showed you previously and learn more about the detailed structure of isothermal supersonic turbulence that is so important for understanding gas and galaxies. And so, you know, in development, one of the things that is really important at the University of Arizona is pushing on the forefront of technology. I just wanted to give a shout out to my student Evan. She's working on a new hydro scheme that works on GPUs. And so what's interesting about this scheme, so if you've used GPUs in the past, the number of floating point operations per memory access is a really important metric. So the more floating point operations you can do per unit memory access, the better. And one of the interesting things about certain schemes in Eulerian hydrodynamics is there really are a lot of floating point operations per memory access potentially. And so one of these techniques is called constrained transport. This is a technique that's often used in MHD, magnetohydrodynamics. And so Evan is implementing a magnetohydrodynamics code on the GPU. And just in a week, she's managed to get a factor of 20 speed up just porting things to CUDA almost directly from PPM schemes and constrained transport schemes that exist already. So there's actually quite a lot of work that we have yet to do, but it looks quite bright, and we'll be implementing this on in a parallel way on the system that we're going to be getting through the NSF grant that I have. Okay, and in closing, I just wanted to mention an important, we talked a lot about big data earlier in the conference. LSST, the Large Synoptic Survey Telescope, this is one of the scientific priorities of America. I know it sounds kind of odd, but it really is. So the NSF and the DOE are committed in some way, not fully, but they're interested in supporting LSST, which is a project to take an image of the sky every 3 nights. Okay, so this will be a remarkable treasure trove for humanity of learning about our universe. It'll be freely available. People will be able to get access to the data. There will be a lot of data. So there will be about 30 terabytes a night of data. That's a remarkable amount. The total amount of raw data will be about 60 petabytes, 30 petabytes reduced in a catalog. These are just the locations of objects, not the images. And the fully processed data will be over 100 terabytes. Sorry, that should say petabyte. I was off by a factor of 1,000, my mistake. So what's interesting about this for Arizona is because we build large mirrors for large telescopes, we've actually built the mirror that LSST is based on here in Tucson, just underneath the football stadium. If you ever go to campus, you can get a tour. And so a lot of people here on the astrophysics on the theory side are really interested in LSST as a data challenge. And so working with the National Optical Astronomical Observatory, NOAO, which is based here in Tucson across the street from the Astronomy Department, we're working on new techniques for analyzing and processing this data, and the University of Arizona Astronomy Department is really interested in building a new data center for hosting and processing LSST data in the future. This project won't be fully online until 2020, but we have to plan now to do these kinds of technical feats in the future. So that's all I wanted to say. Thank you very much. Thanks.
And thank you. It was a very excellent and interesting talk.
Okay.
Any quick questions? Okay. It's Jim.
So my name is Ronald. When you talk about the n-body simulations, you say you do that based on particle. Can you define particle?
Particle. Yeah, it's a mass element. So the details of the way that particles are treated, they're basically treated as point masses with a certain amount of gravity that is softened. So the way that you actually do these gravitational calculations, people may not know. If you've taken a freshman physics course, you know that if you can calculate the gravitational force between two particles just by looking at the distance between them, okay, and then it goes like 1 over the distance squared. But if you want to calculate the full gravitational force of all of the particles on all of the particles, that's an n-squared kind of operation, which is not tractable. So what people do is they use techniques to reduce the scaling of that calculation. One of those techniques, which has been used in a lot of these simulations, is to use a tree. So you build an octree that contains the particle distribution. And then far away particles, you just simply do a multiple expansion based on the structure of the tree to give you what the gravitational force is. So some particles, when you're nearby, you actually do something that's almost equivalent to a 1 over r squared kind of calculation. But things that are quite far away from you are actually treated in a multiple expansion kind of way. So does that answer your question?
Not really. I was
really,
more
okay.
asking about how does it relate to atoms or
Oh, these are much bigger.
Or
much bigger.
That was my question. So
Sorry,
what
yes.
is a particle? Is a particle
Yeah,
a planet?
particle.
Or
Yeah. So in the largest cosmological and-body simulations that have been done to date, the highest resolution ones that have an appreciable volume, they reach about 1,000 solar masses per particle, so 1,000 times the mass of the sun. More typically, it's more like 1,000,000 times the mass of the sun in individual particles. That's why you have to go to these very small scale structures to really measure high resolution regions, like some of the zoomed in simulations that I showed you, and those can achieve better particle masses, but it's just not tractable given computing resources. There's a lot of mass in the universe, in other words. Do you have?
That answers my question.
Okay,
Thank
good.
you.
All right. Yeah.
And Steve?
The minimal spanning tree looked a whole like the type of graph that, at least in other domains, is subjected to graph analytics. Are those methods related?
I'm sure they are, but I think what you'll find in talking to astronomers, we're relatively computer savvy, but I personally have never taken a computer science course. Everything that I learned how to do, I learned in a heuristic way, reading books and writing. So it's quite possible that there are deep connections with what I do in other fields that I would never know. And so you should yell at me and say, oh, well, be smarter about it. But there's only a finite amount of time in the day. So that's, I guess, a general statement. So if anybody says, oh, you're working on an interesting problem, we're doing something very related, here are some techniques that are better than what you're doing, definitely tell me, because I would like to use them. So yeah, I'm happy to talk to you about it later if you know more than I do.
Okay, thanks again.
All right, thanks.